introduction. So it's a super great pleasure to introduce Andrew Fleck, almost Dr. Andrew Fleck, who has been with York for quite a few years, the PhD student, and is now with the TT band in trading. And now he has a very interesting talk about ergodicity and how it's connected to actuarial science. Give it all. Yeah, all yours.
Thank you. Yeah, so I guess this is more, I suppose, for the online attendees. Can we see if they give responses, or can we see if they're responsive? I'll pull up the chat, I guess, if possible. But I guess the way I want to start is who's ever heard the term ergodicity? Is there anybody who's raising their hand on online? I can't see. Is there anybody? No one's raising their hand. Okay, what about the term physics envy? We've heard the term physics envy. Okay, physics envy is a bit of a joke you'll hear sometimes with physicists, where they talk about how economists have tried to construct kind of the mathematical social science sorts, right? And physics, of course, being sort of the queen of the natural sciences for how mathematical it is. They sort of say this with a little bit of derision, right? But what I want to talk about today is this thing called ergodicity economics, where they actually was created by people who are physicists by training, and they actually try to use this concept of ergodicity to solve problems in economics. So, I feel like it's kind of humorous. We've kind of come full circle, right? So before I get started, though, on ergodicity economics, I have to kind of give a quick primer on what the sort of de facto decision theory that economists start around it, and that's called expected utility. And then I'm going to talk about the ergodicity economics, how we can solve some problems that are presented by expected utility. And then at the end, if we have time, I want to talk a little bit about how ruin theory specifically, as part of actuarial science, can kind of offer sort of insights, and there may be potential cross-pollination between the two subjects, right? And how kind of insurers can actually provide some insight here. So to get started, I'll talk a little bit about expected utility. But whenever I talk about this, I always sort of like to zoom way out, right? So when we talk about economics in general, right, we're mostly, and by extension, of course, all of us here who are kind of interested in risk management, finance, and whatnot, we're really concerned with a few questions, right? Ultimately, what we're concerned with is how do people make decisions, right? And then more importantly, how is that reflected, right, in a social context, right? So how do they actually make these allocations socially, right? If you're participating in a market, you want to know how other people are going to behave. If you're insured, you're thinking about how does the risk pool behave? How do I compare against other people? Things like that, right? But ultimately, what it comes down to is how people make decisions, and then how can we think about the kind of social effects of this, right? The reality is, though, is that while this seems very well defined, it is still somewhat philosophical. For most of economics history, it was kind of this branch of philosophy, or that it was, a formal subject, right? So it was kind of seen as, like, for example, Adam Smith was a philosopher studying political economy. He wasn't an economist, right? And but at the same time, financial markets existed, insurance markets existed. People were doing these activities, right? But it was always kind of considered as somewhat more applied pursuit, almost like a trade or something, right? And later in the last century, actuaries were really coming to their own, developing their own tools before this was sort of formally integrated into economics, right? And this sort of started to change, in the last century, right? So coming into the interwar period, and then of course, after the war, you had all these kind of tools that were sort of fused together, right? So kind of the standard paradigm that economists use today with neoclassical synthesis, this is sort of a new phenomenon, right? And they were actually taking together all these different ideas that had existed previously. And one of the biggest one of these was utility, right? It was sort of being put on formal footing, right? And then this was how we were going to have a kind of decision theory that underlay all of this, right? And okay, of course, today, this is, like I said earlier, the de facto starting point for decision theories in economics. The issue is, though, and this is something that I want to point out, is that the practical reality is that finance, the tools that were developed in it, actuarial science, these were things that actually sort of predate this, and that there's actually a bit of I don't want to say a discrepancy, but I think it does influence the way that we think about these issues even today. And I think actually ergodicity economics can kind of help provide some insight into that. But for instance, you had people like Bachelet, right, who had defended their thesis in mathematics, again, not economics or finance, long before this was a formal idea. You know, the beginnings of things like no arbitrage pricing, stuff like that, existed long before, like I said, economics was a formal study. Kramer, you know, was doing his work for an insurance company, but he was a professor of mathematics and he did work in number theory as well. Again, this was long before people were studying these things from this perspective, right? That being said, utility itself is a very old idea, the thing that actually became kind of formalized. So for me, the way I like to explain utility to those who haven't, or who are not familiar with it, is by way of example. Okay, so I guess by show of hands, like in the chat, like who's actually heard of utility theory or expected utility? And is there a show of hands at all, or who's heard the St. Petersburg paradox in general? Is there anybody responding? Nobody? Okay. So the St. Petersburg paradox works like this, right? So we're going to consider a game with a fair coin. Okay, the initial stake starts at $2, right? And you're going to double your pot every time a heads appears, and the game stops when a tails appears. Okay, and you know you always have to pay something to play this game, right? It's a gamble, right? So you know, how much would you pay to play this, right? Would it be a lot of money, right? Is anybody? I encourage anybody to try and respond. If you want to spend any money, anybody here, would you guys spend any money on this? Heard of it? A little bit? How much?
The paradox, as far as I remember, says that if you take the expectation, of course, if the coin is fair, it's possibility.
Exactly. Yeah. So the thing is, intuitively, you wouldn't be willing to pay anything for this, right? Because if we actually go to analyze it, right, probably going to pay tosses with the tails to the negative k. Of course, winnings is just to the k, right? If we actually calculate our expected value minus whatever we pay, you know, we have an infinite expected winning, right? But this clashes obviously with our intuition about how we behave in this case. Most people wouldn't actually pay a lot of money for this game, right? So what is there a possible resolution at all? Well, a very old idea, you know, again, pretty close to when this was proposed back in the 1700s, proposed by Bernoulli, was this idea of utility, right? So rather than measuring your wealth on its own, right, he says, well, what we can do is we can kind of discount it by how useful it is to us, right? So if I have a lot of money, right, this is not going to be, an extra dollar isn't going to mean that much, right? If I have $1 million and you give me $1, right, that kind of marginal satisfaction is going to be very high, right? Whereas if I only have $1 and you give me $1, I double all the money I have, right? So he chose, for instance, just in this case, a logarithmic utility, right? Because it's kind of a slowly, you know, the rate of change is slowly decreasing as you get more wealth, right? And if you apply this to, if you calculate expected utility instead of expected wealth now, your net expected utility now does converge, right? So this would provide some kind of possible resolution, and you could actually kind of solve for, you know, what your C would be, I guess, in this case, right? So it actually provides kind of a way out of this paradox, right? By suggesting that psychologically we discount how much wealth we have as a function of how much we have, right? Now, this was a controversial solution because the problem is that you can't really observe this, right? You know, theoretically it kind of makes sense, but there's nothing sort of scientific here, right? We're proposing, okay, this is how people behave, but what is a person's utility function? I can't just go up to somebody on the street and say, can you draw me your utility function? There had to be a way to kind of, and so as a result, economists were generally kind of skeptical of this, and there had to be a way to kind of make this operational and make this scientific. And that's why I was saying it took till the mid-century to do this.
If they discount, you don't have to resolve it with the utility function. Actuaries usually resolve it, as far as I know, with just discounting. Just discount the value.
But how much, okay, but even if you discount, right,
then
how much?
Assume that you know the effective interest rate, you know the delta,
Okay.
and that's it. Some converges.
Right, but do people always discount using just the effective interest rate?
Oh, that's a different story, but
Right.
that is less controversial than if you use utility that you don't observe.
Of course, right? But again, like I was saying, right, the intuition that actuaries have is a little bit different too, right? But also, yeah, you're right. You know, you could just approach it with temporal discounting as well, right? The main issue is that we wanted to see is there a way to kind of make this scientific, right? So in the 40s, you know, von Neumann and Morgenstern came up with this powerful theorem, right? And basically what they said is, we don't have to study the theorem in too much detail, but basically you get these four axioms, right? That they propose for kind of reasonable ways of ordering random variables, right? So if each random variable represents sort of a gamble, like the one I mentioned earlier with the St. Petersburg paradox, right? We would expect, you know, We'll always prefer one gamble to another, or we'll be indifferent. You know, we'll have transitivity, you know, that seems reasonable. You know, we should always be able to approximate, you know, gambles by close ones, right? They should, you know, there should be a sort of a notion of closeness there. And then of course there's this idea of independence, right? Which is the one that's relaxed the most. But basically the idea is that, you know, if I have a gamble, you know, if I have a gamble that I prefer to another and I add something to both in some respects, I should still kind of preserve the order, right? They then said, okay, if we have this kind of set of this axioms over preferences, then we can actually show that expected utility will you'll be able to map your preferences onto expected utility and vice versa, right? So if I prefer one gamble to the other, right, then my expected utility functional for the first will be greater than the other if I prefer it, right? And this was huge because the thing is that you can observe these, right? You can actually observe people's preferences. So if I wanted to be more scientific about this, right, I could offer people a menu of options, right? And I could say, okay, I want you to select between the gambles that I'm offering you, right? And then I can observe the choices they make. And then, you know, I could try to start talking about things like utility in a more scientific way, okay? Now, obviously, the story is more complex, right? Do people actually follow these axioms? You know, like I said, independence is often when it's relaxed. That's how you get these kind of Choquet expectations. That's how you get, you know, things that look sort of like insurance premium principles. But this is proven to be kind of the very popular kind of starting point for most economics research. And it sort of forms and it's gone on to kind of form the basis for most financial economics, right? So the sort of starting point of any theory for financial economics basically says, okay, I'm going to have the sum of utilities over time discounted by something. I'll have a budget constraint. You know, so if I have some group of people who have, you know, they have the choice between some basket of goods over time, you know, as long as I specify some utility function, I can solve this maximization. And again, you know, if we know that people's preferences are reasonable, they follow these axioms, we know that this is justified and we can use kind of a utility function, right? And this isn't just some kind of abstract theory. I mean, it is, but it actually informs reality, right? So if you look at the previous slide, right, and you look at this equation here, if you go to look at, this is sort of, this book, the name of the book escapes me at the moment, but it's by Jordi Galley, and I think it's called Central Banking or something. And it's sort of the Bible among central bank policymakers. I actually know someone who works for the Bank of Canada. He heard of this book, but the person who originally showed me the book was somebody who works for the Central Bank of Chile. And if you look here, like the equation one on the right, that's literally what it just had in the previous slide, right? So while this is like an abstract theory, it does actually inform reality. The way interest rates are set, you know, the way these things are computed, you know, very much is informed by this kind of expected utility framework. And for us, for kind of RISC people, it's hugely important, not just for the interest rate aspect and for, you know, the policymaking aspect, but it also underlies a lot of the ideas behind asset pricing in economics. So if I were to kind of take the equation I had and reduce it to a simpler case, where I only have two periods with one asset, and I do this optimization, you know, I can actually solve for the price today in terms of this expectation of the payoff tomorrow, where I discount by this kind of stochastic discount factor, which is related to the marginal rate of substitution. So, you know, the idea then is that, okay, my utilities, you know, my preferences should inform my utilities, which will then in turn inform how much I discount, you know, random events in the future, right? So it's not just for policymaking, it's also for asset pricing and all the other things that we might be concerned with. The question though that this begs is, again, you know, it's more scientific maybe than it was before. People should be less skeptical. But how scientific is it really? We can observe preferences, but this is supposedly a model of human behavior. So we should be able to test it behaviorally, right? And so it seems that the central question for a financial economist should be, well, what kind of preferences, if they indeed follow these axioms we mentioned earlier, do people have? And what kind of specific utilities do they actually possess, right? And the question I ask is this a central research question? And the answer is sort of. Obviously, there's a great deal of interest in it, but the reality is that, like I was saying, if you're a central bank policymaker or whatnot, you often will take a specific utility first, and then you kind of work through the problem from there, right? So it's sort of a research question, but it's not as emphasized as maybe you would expect. And there are reasons for this. So for instance, like going back to what I was saying earlier, we're often concerned with social issues, right? We're concerned with what happens when there are many agents interacting on a continuum, right? So I liken this to, again, talking about physics MD, I liken it to the n-body problem in physics, right? You know, if I have two, planets orbiting each other, everything is fine. But if I have three, I have to make some heroic kind of simplifications to make everything work. And even then it's an approximation. If I have more, it just becomes totally chaotic, right? So if I have a million households in an economy, right, I have to make some pretty heroic simplifications to make the analysis work. One of the classes of utility that makes this work is your HARA utility, given here below. This kind of delta is a sort of a measure of, I guess, subjectively people's risk preferences, how risk averse they are or whatnot. But the important thing about this one is it allows you to actually do a lot of the kinds of, actually just go through the kinds of problems I was talking about earlier, right? This simplifies things considerably. It contains things like exponentials, logarithms, powers, etc. And you can actually do the analysis in a way that you couldn't do before for many, many, many agents. Right. One of the problems though is that when we do this, when we use something like hard to model individuals that we aggregate, when we compare the results, we often get contradictory results. So if we were to model a whole economy using agents of that kind, right, and then we compare it to people's behavior individually in like a laboratory, there's often a contradiction. So a famous example of this is the equity premium puzzle, where they look at consumption in the economy based on models of this kind. And they say, okay, well, it must actually lead to counterfactually high levels of risk aversion that we observe, right? So there's some kind of disconnect here, right? And of course, some people have said, well, maybe the problem is actually utility itself, right? And this is where kind of behavioral economists come in. So you have like Kahneman and Tversky and their prospect theory and things like that, where they've tried to kind of modify this theory at the level of preferences, having things like framing effects and stuff like that. But I would contend, and this is where a lot of ergodicity economics gets its motivation, that maybe we're working in a bit of a circular fashion, right? We're saying, well, preferences give utilities, which then can define preferences, right? So we say, oh, well, people have these preferences because of this utility. Which preferences do they have? Well, they have the preferences that are given by the utility we're modeling, right? And so you're kind of working in an unscientific way. You're kind of pulling yourself up by your bootstraps, right? And you're sort of working in a circular fashion. And then the question becomes, well, is your theory even falsifiable at that in a real scientific sense, if that's what you're doing? And that's where the motivation for ergodicity economics came from. I highly encourage anybody who's interested to read this quick summary in Nature Physics here by Ole Peters. He's sort of the father of this, right? This is sort of his overture to anybody who's interested, where he talks about how we can actually start to think about these problems in a more scientific way by using ergodicity. And that's what I want to talk about now, which is ergodicity economics itself. And again, I like to do everything by example. I like to motivate everything by example, especially for those watching at home, right? So I'm going to present two very simple kind of games or examples, okay? So in the first one, we have an additive wealth dynamic, right? So we start off with some wealth, and then every time we're going to add a random amount, okay? And in the second case, we're going to start off with some wealth, and I'm going to multiply it by some random amount. So you can kind of think about this as sort of being like an additive return. This is sort of like a multiplicative return. If you want to think about it in real life, this would be like getting paid a wage. This would be like investing in the stock market, let's say, right? And what we want to do is we want to ask the question, what is the long-term behavior of our wealth under these dynamics? Okay, so let's say R is something very simple. It's either 0.6 or 0.15 with probably half each, right? It's like, is this an expected value of 1.05? So in the multiplicative game, it's like 5% return. That's typical for bond or whatever. In the additive game, what we can do is we can just simply look at the sum, right, of our wealth, like the sum to get our wealth over long periods of time. If we choose for a very large n, we can just take the expected value. We'll just have n times the expected value, right? So our long-term wealth will just be x naught plus n times 1.05, okay? So we have a linearly growing wealth kind of in our long-term view, right? So this makes sense. It's additive, grows linearly. In the multiplicative case, we can kind of apply our law of large numbers in a different way, but what we can do is we can show for kind of our long-term behavior of wealth, it should actually probably decrease, right? We'll have our initial wealth times, in this case, 0.95 to the power n. So as n gets larger, we should actually be kind of shrinking our wealth over time until it basically goes close to zero, right? So this would give us a sense of the long-term behavior of these games. But what about the expected value of our wealth, these games, right? So in the additive case, it's simple, right? We take our expected value, we get the exact same thing as the long-term behavior, right? We get basically just n times 1.5. That's kind of our linear growth of wealth, right? In the multiplicative case, we get a kind of a different thing than we had before, right? So we have our initial wealth with a 5% return, like 5% return to the power n, right? So what's going on here? In the additive case, we have the same behavior. Our expected value is sort of the typical behavior of our game. But in the other case, in the multiplicative case, before the typical behavior of a single path would be to go smaller, but here our expected value is growing, and it's actually growing faster. And I think you can get a little bit of insight as to why or how this would be happening if you look at a couple of simulations, right? So I'm going to do a very quick simulation of the additive game. So that once there. Right. Here we go. So this would be this is what the kind of paths in your additive game would look like, where the black line is your kind of expected value, right? So your paths kind of hug very close to your expected value. It does give you sort of a typical outcome. If you look at the histogram of final wealth, right, they kind of cluster around your expected value. Everything kind of works as you would expect. But if you look at the multiplicative case, right, what do you get? You get some paths that get to go to extreme levels of wealth, right? Where most people, actually hug pretty close to zero. And there's actually one graph I think that really shows what's happening here, where in red, I have sort of the maximum wealth of a single agent, right? Divided by the number of samples, then I have the average wealth. And as you can see, the behavior of the average is very much driven by kind of the richest participant. Like if I'm doing an ensemble, like if I'm running many, agents at once, right? So the idea is that, if I were to look at kind of an ensemble, if I were to run this simulation a bunch of times, right, and I were to take an expected value, it's really going to be dominated by the most successful participant, right? But most people are not going to do very well at all, right? And this is sort of one of the insights that they try to talk about in RISC economics. They say, well, as humans, we actually have to live our life through time. We can't access the ensembles around us, right? Like if I'm taking an average of outcomes, right, only one of them is going to happen to me. And only one path through life is going to happen to me, right? I can't live a parallel life, right? So the idea is that, the average may not be the most informative thing for me as an individual, right? So what does that mean for us, right? Well, this is just the intuition and simulations. It's just what I was getting at. So in the additive game, of course, the expected value gives us a typical path, only in the additive case. It doesn't give us that in the multiplicative case. So we wouldn't want to use an average for the expected value in the multiplicative case. This wouldn't be informative to us. So we want to think of a way of rescaling the wealth to make them less significant, the large wealth cases to be less significant as the low wealth ones, which are much more common. Right? And of course, we return to the idea of utility. And in this case, we can just use log wealth. So if I look at the log wealth of the multiplicative game, the typical case, right, if I look at the long-term behavior, will match the expected value. Okay, great. It's like our St. Petersburg paradox. But what is this actually telling us? Well, the economists would think of this as a utility function, which rescales, our wealth preferences or risk tolerance, right? the risk in the risky proposition, we have high wealth, right? We rescale it to have let's say order of magnitude. But old Peters in the ergodicity econ community, they say, well, actually, if we have a dynamic, what we're measuring here is actually a growth rate, right? The log wealth in this case would give us something that looks like a growth rate of our wealth, right? It's multiplicative, so we use log to measure it. And they say that's what we should actually be looking at. So they say, so just as a quick preamble, an ergodic observable is one where if I have a stochastic process, right, this is like the kind of physicist idea of ergodicity. If I have a stochastic process, right, and I take an average, I sample it over time, right, I observe like a single path over time, and I take an average, right, I'm going to get, and assuming it converges, right, I'm assuming a lot here. We're going to assume it converges, everything works nicely, right? Then I'm going to get something called the time average, right? So I'm averaging path over time, right? But if I take independent copies of the same stochastic process, right, at a certain time, right, I can just take my expected value, right? And they call this the ensemble average, right? So there's two notions of an average, right? So if I'm looking at a stochastic process, I can say, okay, the next step, what is my expected value going to be? Or what is the average going to be over the lifetime? This goes to the kind of typical behavior risk ensemble I was talking about. They say an ergodic observable is one where these things are equal. All right, where the typical behavior of a path will give me the same as the ensemble average. So the classic example in physics is when we talk about temperature. So if I look at a particle in like a box, if I look at gas, for instance, right, a bunch of particles in the box, the time average of something bouncing around the box will be the same as if I were to kind of take an ensemble average. And that gives us a well-defined notion of temperature. That's how physics works, right? And they say, well, what we can do is we can look at a growth rate. So we can look at the change of some quantity, right? So we'll look at kind of our delta, and we'll call it nu now instead of utility. We'll say delta nu x over some time increment. We'll say that this is a growth rate at some point in time, right? And what they say is that a meaningful growth rate is one that's ergodic. The idea being that if we look at the path as it goes, a typical path, or if we look at an ensemble, we'll get something that is still informative, right? So this is a good notion of a growth rate, they say. And there's some justification behind it, and there's some debate about what it could possibly mean. But the idea is that the expected growth over one increment should be the same as, assuming everything is kind of stationary, it should be the same as over a typical path to be informative. And what they suggest, right, is that agents actually want to maximize a growth rate. So it's the growth rate is the thing that we're actually interested in, not utility. So this nu that it constructed used to construct your growth rate is what we should be looking for. And then, of course, like that was in a discrete world. I prefer to work in kind of the continuous time world, right? So if we have our meaningful growth rate the same way, we should get what they call the ergodic axiom as I've written here, right? So kind of our time average should equal our ensemble average, right? So if I have a dynamic, if I have X, see some stochastic process, this could represent my wealth, I should be looking for this nu where this is true, right? And what they claim is that this is actually how an agent will behave. This is actually what an agent will be maximizing over. So a couple examples, right? We can start with just a simple Brownian motion. This is our additive dynamic, right? And of course, if we make a linear, we choose our kind of linear utility, right? Our nu equals X, then our time average and our ensemble average are both equal mu in this case, right? Everything is nice. Another example would be, like we even talked about this in the discrete case, but in multiplicative wealth dynamics, if we have a GBM, kind of the starting point in finance, then we make our choice of log X and we can show our time average and our ensemble average are what you would expect. So mu minus sigma squared over 2, the volatility facts. Everything is fine. So if I were exposed to a geometric Brownian motion, this log is what I should use. If I was exposed to an additive wealth dynamic, I should use a linear utility, right? And of course, you can get some other examples, right? So they say if I'm exposed to this dynamic, this strange looking one here, where my fluctuations actually shrink with the more wealth I have, that I should have an exponential utility, but not the one you're used to seeing. This one is actually risk seeking, right? So if fluctuations decrease with wealth, I should actually be wanting to take risks, right? And then they say if I took it the square root utility, I can get something that kind of goes between, for low wealth, it looks additive, for high wealth, it looks multiplicative. This is sort of the Kramer square root. So the basic contention here that they're trying to drive at, though, is that, you're removing a certain level of subjectivity from the modeling. If I have a dynamic of wealth, I should be able to find this mu that gives me a growth rate. And that's actually what agents are looking for, right? What's incredible is that this is now very testable, right? You're making a very, very, very clear proposition. You're saying, if I expose agents to a certain dynamic, they should want to maximize their growth rates, and the growth rates be interpreted in kind of a utility function sense with this mu, right? And I should be able to observe this. Importantly, what I should be able to observe is if I present an agent with one dynamic, and then I present the same agent with a different one, their utility should observably change if this were the true case, right? And in fact, this was tested and shown to great effect in this experiment with these psychologists and neuroscientists in Copenhagen, right? So what they did is they took these agents, they said, okay, we're going to show you some pictures. Every time a certain picture is shown, you're going to get a certain level of wealth. They're not actually told what's generated. They're not actually told if it's an additive or multiplicative wealth. They just have time to learn this, and then they have to make decisions as a result, right? And then they try to observe their utility function. And then on a different day, they would show them a different dynamic, but also, again, showing the pictures of different time to learn. And I love this picture because this is a sampling of some of the results. So each graph is a participant where the kind of these distributions are sort of the, I guess it's a Bayesian distribution of what the researchers think the risk aversion is for each agent. So going back to that kind of hard utility I was showing you earlier, if your risk aversion is at 0, you get kind of a linear utility. If it's at 1, you get this logarithm. And the idea is they said, okay, if we present them with an additive one and then we switch it to a multiplicative one later, we should actually observe their risk aversion change. We should actually observe that the utility they're using will change. And in every single participant, you can see this shift. So they proposed this very simple hypothesis. They said agents want to maximize their growth rates. Utility is sort of informed by that. But importantly, it should change based on the dynamic you're exposed to. And then change the dynamic and observe exactly the shift that they anticipated. Right? And in fact, there's actually been more research since that has kind of gone on to confirm this, right? That they keep observing this shift over and over again. The other thing too is, and I don't have time to get into everything, is that even just starting from this very, very simple framework, right? Because think about it, if you have a dynamic and you can specify the utility the agent will use, it removes a great deal of ambiguity in modeling, right? So they've taken this idea and they've tried to apply it to other things. And they've been able to produce these incredible results, right? They were able to produce a theory where noise comes from in financial markets. They were able to predict, when insurance contracts would exist. By analyzing growth rates of an ensemble, sharing, pooling resources versus individuals, they could explain where cooperation comes from, analyze inequality, so on and so on. For us in particular, they have a great paper where they talk about the micro foundations of discounting, right? So they have different dynamics that each agent is exposed to, and then they find out what the discounting function is. So Dr. Furman, you were talking earlier about how you discount, right? Like what interest rate or whatever. And they were saying, depending on the kind of wealth dynamic we show them to, they can actually change how much they discount by. So they're actually, a lot of things that you see is behaviorally is, a hyperbolic discounting function. They're able to derive it under certain cases. Under certain dynamics, you would want to use a hyperbolic discounting function. In other cases, you discount linearly. In other cases, you discount with classic EPR, right? So they're able to show when different agents apply this. These are all links. So if we can post the slides, like people can click on each one of these papers in here, right? And I think we got about 5 minutes left, right? So can we take
10 minutes.
10 minutes? Oh, perfect. Okay. So this is sort of the idea behind ergodicity economics, right? So it's the thing I really like about it is it's very simple, right? The ideas behind it are extremely simple, but you can go very, very far with it. But the main thing is that it intuitively kind of makes sense. It sort of moves away from the abstractions of preferences and utilities, and it looks at an agent existing in time, right? It says, as humans or agents or firms or whatever, we exist through time. They're like one of us, right? So this actually kind of sounds very familiar to people who have studied actuarial science, because there's actually a similar framework in actuarial science. This is called ruin theory, right? And it informs a lot of the understanding behind actuarial science, right? It's a very old kind of classic way of thinking about risk. But it actually kind of comes from a very similar place. And I think it's notable that it came from this place before kind of utility and economics became more formalized. So as kind of a quick crash course, right? We're going to consider just the classic Kramer-Lundberg model, right? So you have some premiums I'm collecting with premium rate P, and I'm collecting them at PT over time. And I'm going to have some compound Poisson process with some losses X, and these represent just random losses that come at random times. Right? I'll have some surplus ZTs, right? So this is going to model kind of an insurance company, but we can be a little bit more open-minded. This can model lots of different situations, right? People like to collect, people make money over time, but they're exposed to random losses, right? And we'll define our the ruin time as the stopping time where this falls below zero. And then the probability of ultimate ruin being the probability that this happens at some point. And then of course, this informs kind of our premium calculations, because we can say, well, if we're not collecting more than the net premium over time, we will eventually go ruin probability one. So we need to add kind of a safety loading, and this kind of is where when we calculate premiums, this is sort of where that idea comes from. Right? We're very lucky because in this model, we actually have a way of approximating the ruin probability very easily. It's just going to be bound above by this exponential function as a function of the initial kind of wealth we have, and this R, which is comes from the MGF of the compound losses, right? So I'm going to kind of just go over those details. I'm not going to go over those details. It's very straightforward. This is why the model is very, very useful. And what we can do is we can kind of bound our ruin from above by some kind of subjective amount. We can say, well, we're comfortable with the probability of ultimate ruin being some very small epsilon. And then if we invert this to find premiums, we get this kind of this equation here involving the MGF. And this is called the entropic risk measure, right? What's interesting is that we also have a way of interpreting it in utility, where we say, if I have an exponential utility and then I calculate my risk principal using that, then I also get the same thing, right? So in this case, if I have this dynamic and I use this utility, right, I have a way of explaining what this actually means. An agent who would use this utility under this dynamic would be concerned about risk and trying to ruin, would be concerned about ruin and trying to minimize risk. This actually sounds very familiar to ergodicity economics, because they say, well, I'm an agent, right? And I'm looking through time, and I'm concerned about the growth rate of my wealth, right? I can only live my one path, right? Here we're saying, okay, well, I have this, and I have a utility that forms that. Here we're saying I have some utility potentially that what I can interpret as, again, something related to how I go through time, right? So this exponential utility here is telling me I don't want to be ruined with probability, epsilon over time. And so there's actually a very kind of, they're very operational. They're very kind of intuitive, right? And so my thinking is that there has to be some kind of relationship, or there has to be some kind of connection, right? Because they're intuitively coming from the same place, just from different directions. One's concerned with growth, one's concerned with ruin and loss, right? So, they're, like I said, they're both operational and they're both time-based, right? So the main thing is that in both theories, you're removing a certain level of subjectivity from the modeling, right? An insurance company may have a risk appetite, sure, but it's informed by going bust, right? What they're saying in ergodicity economics is maybe there's a certain level of subjectivity somewhere, but it's mostly you're concerned with growing your wealth, right? I think there should be a way to combine them, right? If I were to try and do this though, if I were to look at an ergodic interpretation of the Kramer-Lundberg model, right? And I were to calculate the utility that would give me a growth rate, right? I get the linear utility, all right? Well, what we could think of is that maybe tells us that the net profit condition, right? The idea that I need to collect more than my net losses maybe has an ergodicity economics interpretation, but there is sort of seemingly kind of a contradiction here, right? Because I have an exponential utility with the ruin theoretic way, but I have a linear one with the ergodicity way. One way I think about possibly resolving this is, what if I take n identical individuals who have basically the same wealth dynamic as the insurance company, but I divide it by n. I say that, we just, when I pool them together, I'm going to get that dynamic I saw earlier, right? So basically, the losses happen less frequently. And I have I'm collecting some interest, like in this case. So you can think of this, like I said, it's like a firm, making some money, but I'm subjected to random loss, right? And then I can pool it together and I can recover the insurance company's risk index. So the idea here that I'm trying to get at is that we can now think of these guys pooling together their wealth and then having the model we had earlier. So I take some companies, right? Without coverage, they're exposed to some stochastic losses. They have some compound losses, right? And then I have an insurer who just has some money, he doesn't have anything, right? But with coverage, I've eliminated the risk for the company, and I get my CL dynamic for the insurer, right? And I can talk about the growth rate from both using that E interpretation. And I can see, well, the companies are lowering their growth rate. The people who are buying insurance are lowering their growth rate, but the insurance company is increasing it, right? Conversely, in the case with and without coverage, my individual companies, my individual participants who are buying insurance have eliminated the risk of ruin, right? Whereas the insurer has taken some on, right? So the idea is that, maybe for the individual companies, right, maybe they don't have as much money to initially start with, they don't have such initial capital, then they, maybe their risk of ruin wasn't negligible, now it's zero. And maybe because the insurer started with so much, he has enough to make that risk of ruin negligible, right? So what we have then is we have that insurance will lower the growth rate of some of the company buying insurance, right? While increasing the insurers, right? But we've also eliminated the risk of ruin for our insurers and made it taken on a small one for the insurer, right? And what I think is that basically these two things kind of have to exist in kind of a balance or trade-off with each other, right? So EE tells us that, okay, we want to maximize growth rates, but it feels like a somewhat incomplete picture. And in fact, this is actually one of the criticisms that EE gets, right? They say, well, if it's all about growth rates, you're talking about how people live through time. You're saying this is all about growth rates. People aren't just concerned about that. They also are concerned about whether or not they're going to survive to the end of, their lifetime or whatever, financially, right? So what I claim is that, okay, well, if you maximize growth rates, it's not that consequential if you face ruin, right? But at the same time, you're never going to just minimize ruin because you'll always be outgrown by your competition, right? It's like when you're investing, right? If you only ever invest in bonds, then the people who are also investing in stocks will eat you alive, right? So my conjecture is that some of these shortcomings can be complemented by some of these insights from actuarial science, and that we can actually kind of have a more complete theory that way. And I think that actually what you can do is you can use this to kind of create a very simplified model of how capital would actually flow through the economy. So high wealth individuals and institutions will cover the risk of low wealth ones for the cost of a premium. So the high wealth people, they'll get an increase in their growth rate, they'll have a negligible risk of ruin. The low wealth people, though, will not be worried about ruin, even though they're giving up maybe a slightly higher growth rate, right? And the thing is that this seems very intuitive and it seems very simple, right? But there now is an analytic framework to kind of think about this. There's a way of actually doing modeling with this framework in mind. No longer would we be just concerned with, specifying utility work model. We'd actually be starting from what these people's preferences actually would be, keeping this in mind and then working through it. And I hope what you can do with this is you can kind of explain, all sorts of things, right? So, hedge funds in this case would be thought of as insurers covering your income. I mean, they almost explicitly are that. You could explain, the cost, why there's a low cost of capital in insurance flows and how it drives so-called alpha of certain investors like Warren Buffett, and stock pickers generally. And I hope it can be applied to other puzzles, right? EE has given us insights into the equity premium puzzle. Maybe it can be applied to the annuity puzzle, right? There's interesting dynamics that annuities have, right? That are slightly different than other financial products. Maybe this is where some of the puzzles come from. So that's it for me today. But basically, I just want to leave you with this conclusion, which is that we have a notion of what our decision trees should look like. What's lacking is a unifying scientific theory explaining the specifics. Why do people have certain utilities? Why are people making the decisions that they're making? Ergodicity economics is attempting to tackle this by using growth rates, right? We already have a notion of it as well. In fact, actuarial science is probably fruitful. My own work in this area is concerned with how to do pricing in this area, right? Nobody solved this yet. There's lots of open problems, you know, in this area that could prove very, very rich for veins of research. So I'm trying to basically today evangelize to kind of a RISC audience of the possible benefits of studying ergodicity economics. I hope I succeed. So thank you for your time.
Questions? So that's intuitive. Or what you mean by intuitive?
Any question?
So the graph showed for most predictive growth, right, where some of the paths dominates others. But eventually every path will converge to zero, right? So it's probably one, every single path will go to zero eventually.
Yeah, because you eventually, the typical path will shrink down.
And it's like the underground emotions, right? If mu is less than sigma squared,
Exactly. Yeah.
converge to zero, but the mean goes exponential. So this ergodic observable thing. So lots of stochastic processes are not ergodic.
Yeah.
So what do you do then?
Yeah, so this is actually kind of a criticism, I would say, of ergodicity economics as they think about it, right? Because they're coming at it from kind of very physics perspective, right? Where the other problem you have is that some processes are so strongly ergodic, right? That any function of them will also be ergodic, right? So a classic example would be like the OU process, right? Any function of that would be ergodic, right? So what would be the meaningful growth rate in that case? It's not unique, right? So I think that and this is actually what I was saying, this is when I was trying to do some of the pricing work, I was actually trying to kind of solve some of these issues myself. It's still very new, and they don't exactly have very strong kind of mathematically like rigorous definitions for like, a lot of these ideas yet. So you know, you run into the opposite problem you're mentioning. Sometimes the growth rate won't be right, and then sometimes you won't actually even be able to find, you know, a function that makes it ergodic, right? And then, like you were saying, you know, so there are open questions here. Like, I'm not saying that this is like a solved subject yet. Right? So,
We have some questions from chat as well.
yeah.
A lot of questions.
Oh,
So in all the discussion, it seems like it's a big assumption that utility is constant in time. So basically, whatever utility I have now, I'll have roughly the same utility tomorrow, year from now, right? That's like human behavior, right? It changes like this from instant, right? I was reading successful with studied how people lie, and it was amazing. So they primed people, say, by making people think about something good, let's say, read them a passage from the Bible. The probability of lying just decreases like dramatically.
right.
And then by making people think that someone else is lying or someone else is cheating,
Right.
the probability of lying increases dramatically.
Right.
So basically, you can prime people into changes their perception of reality, and this changes their utility just like this.
Yeah.
So basically, my utility could be 1 in the morning, different this afternoon.
Right. But what's interesting to your point, right, is that what they're basically proposing is a mechanism for why it would change. Right. So people's utilities do change through the course of their life, but the dynamics of wealth that we're exposed to also change over the course of our life. When we're young and early in our career, we're making lots of money, we have lots of investment opportunities, right? When we're older and we're retired, we're withdrawing a lot, right? So the kinds of wealth dynamics that we're exposed to change. To your point about lying and cooperation, right? Sort of talking basically about trust and cooperation, right? They've actually done some stuff, like they've actually done some work with this idea in ergodicity economics, where they say, you know, if you have a dynamic where you're pooling resources, right? You can show that cooperation becomes favorable under this framework, and then it won't in other cases. When you're talking about priming people for lying, in a way, what you're doing is you're kind of giving them a sense of what the dynamics are around them, right? So if the dynamic is changing, then yeah, their utility function will change accordingly, right?
Or thinking about something good like in the Bible, that's also telling something about reality, like
Right.
changing your own inner
world, yeah. But then it could also be informed, but in that case, it could also be informed by what you think other people might do, because of how you're into it, right? So, and I mean, it doesn't have to be the end all be all, right? There is still room for subjectivity in a theory like this. They're just saying that if you start from a place where you can remove a lot of it.
I think like this suggestion about going out this way, asking random people about what's their utility function.
Yeah, well, but this is a well-known, I mean, this critiques about that we don't know what the utility function is. This is when we, for example, talk to students about how we price like contingent risks. We always say that, maximizing utility is not a great way, but we never, even the economists, they never say, well, we do all that, for example, for exponential utility. When you started with the expected utility framework, they say, okay, whatever we prove for this set of preferences, which is correct for all utilities and set of utilities. And then they do examples, of course, but whatever their statements are, they apply to any utility in the chosen set of utilities. So I'm not really, I don't entirely agree with that it's for a single utility what they derive, right? They usually say, okay, if it's for every utility, so the conclusions are for every utility in the set. If you agree with the preferences that led to how this set is shaped, then you must agree with the conclusions. But here is a numerical example, right? But my question is,
but just because you're up to sorry if I can interrupt, right?
Sure.
Often there are some very, not hidden, but they're sort of glossed over assumptions over what kind of class of utility function you're working in, right? So for instance, you're usually assuming agents are risk averse, right? They have like a concave utility, right? But I showed, for instance, if you have the right dynamic, this would predict that agents are sometimes not.
No,
right?
well, this I do agree. I totally agree that utility also changes over time.
Yeah.
And et cetera. I'm just saying that, in my opinion, it's too strong to say that economists do it just for one utility.
Yeah, you're right. I'm maybe being a little unfair.
But my question is this, maybe I don't understand something, but speaking about annuities, right? So you mentioned annuity puzzle, right? So I was trying to think about how I apply this entire idea to the annuity puzzle. So usually what actuaries do, they compute the expectation, right, of this annuity outcome. And this is, I guess, something that you call ensemble, like the usual expectation with respect to this X omega, right? How do I compute the time expectation?
How the utility, right?
Yeah, how not the utility, forget about the utility, I don't want the utility anymore. I want to try to apply your technique, right?
So
because you started with this equation, right? Where the expectation with respect to time, I guess. There was a limit where t goes to plus infinity, I guess, 1 over t and integral 0 to t, blah, 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 right? So how do I compute this? Because I don't really know. The idea that actuaries usually use is that, okay, you have a mortality table, this is coming from a cohort of people, so this is the ensemble, right? And I sort of know, yes, I don't know my own path, but at least I know how to price my annuity with respect to this ensemble, the mortality table.
So
how do I do?
Well, I actually tried to do this with annuities in particular, right? And I don't know if I got anything that was super interesting, but I did try this. So what you'd want to do first, you'd want to specify the dynamic for the utility, right? For the annuity, right? One of the issues that the kind of classic or like original EE people have, right, is that the stochastic crosses, like I said, that they're dealing with, like when I was talking about Lexi, are very, very restricted. So some of the work that I was trying to do was kind of apply this to a larger world. And one of the things that you need to add is you need to add stopping times. Because for an annuity, right, you get paid a certain amount of wealth and then you're done, right? And that's the end of it. So I tried to add kind of stopping times into this framework and then kind of change the axioms a little bit to incorporate this, right? And I think I made a little bit of progress, to be honest. But we can go over it later. But the point is that you would need to, the framework I showed you wouldn't work.
Yeah, so the t will not go to plus infinity, it has to stop somewhere.
Exactly.
But you also have to assume a certain mortality dynamic, and then you have to derive your wealth dynamic from the mortality dynamic, right?
Exactly. So
but Andrew, here's the trick, I guess, right? You have to assume that you know your mortality dynamic for you, right? Well, for the person that you do it, but isn't it a big
ask?
Exactly.
Yeah. I mean, I guess in that case, that's where subjectivity would come into play, right?
Exactly. It's a big subjectivity.
Yeah.
Even the mortality table for a cohort of, lots of newborns is subjective. But here I want to know precisely what is mortality dynamic for one person.
You'd have to ask them what their perception of their mortality dynamic would be, right? And assuming you had a good model of that, then you could apply what I was talking about, right? So I'm not saying there's no subjectivity, because the key thing to keep in mind here is that assuming you get over some of the issues I was saying about some stopping times, and I can show you if you want. I have another talk that I gave at like the EE has a conference, right? And I gave a talk at this conference talking about this, where you have to add stopping times. Assuming you can use that framework and everything still works out, right? What you're getting at is still where subjectivity would come to play here. It goes to Alexi's question, right? Because a lot of this has to do with how people perceive the dynamics they're exposed to, right? So what this is basically saying is that if you perceive your dynamics one way, you're going to behave a certain way, but that perception is subjective, right? So to your point, you know, maybe that, I'm not saying this could resolve the puzzle like a silver bullet, but it might help get some insight, because it might actually inform, if you assume this hypothesis is true, that you could back out what people's subjective perception of utility, their mortality. Does that make sense? Or
Maybe. I don't know. It looks to me that the beginning where I started about is probably better suited for physics, where you have this gas motion or whatever, rather than something as complicated as mortality in the case of a new EEBOT.
Yeah. So it could be that case. Yeah. I think. Yeah. I suspect though that there's still a way to do it. I can show you some of the stuff I worked on before, like because like I said, I have another talk where I talked about how you handle some of these issues, and then maybe we can try to find like some way to work through it. Because I think once you've specified the dynamic that you would have with it, right, you should be able to apply. You should be able to apply this still.
Yeah, no, I agree that if you are able to specify the dynamic of the mortality, then you will have this process, then your wealth process will be connected to the mortality process, and then you will take your averages. And yes, it complicates things because you don't know when they die, so your teeth cannot just go to plus infinity, you have to stop somewhere. And then maybe Alexei knows how to do it, no, because it becomes tough mathematics.
Yeah.
But still, you start with this very subjective assumption that you know the mortality process for one individual, right?
And maybe people have wrong ideas of their mortality.
And you know this mortality process from today until the end of their life.
Of course,
if you make if you make fun of economists and say, well, I know the utility function, and here it's even worse, I guess, right? How can I know my mortality?
But the key thing here is though that in a way, what this framework would allow you to do is kind of organize your subjective assumptions, right, more explicitly. Because the thing is that with the economics, when they're using expected utility, right, you have a certain level, you have a degree of freedom in the modeling with your utility that you're choosing, as well as the dynamic, including the mortality, right? So when you get a result, you're not actually completely sure where the result is coming from. Is it from the utility I specified? Is it from the dynamic I specified? Here you kind of removed one of the elements of it. You've made it kind of fixed, right? And so now you can kind of study these things more directly. Does that make sense? Or
I'm thinking that you can probably say, okay, for a typical mortality process, whatever it means, right? This is the sort of the solution. And then this is how what actuaries do, which is the right-hand side of your equation, compares to the left-hand side, which is what I believe the consumer does, right? Based on what you said. For a typical, or maybe a set of typical mortality processes. And then maybe this typical set comes from maybe it's sort of shaped by the form of the force of mortality. Because, for example, we believe that the force of mortality starts from, well, it decreases first, and then, because you know this buffed up mortality, right? Force of mortality. Then maybe this is how you can sort of motivate this.
When I did, I can show you. I guess I'll show you later, because I think now that I piqued your interest, because what you do is
I wasn't anticipating this because I didn't have time to read about it.
Okay.
But you were talking about it.
Yeah, well, I'll show you, because I guess this was sort of my goal here today was to evangelize. Right? I was watching. You guys want to show Mad Men? You want to show Mad Men? Right? Has anybody ever seen it? Yeah, you've seen it. Yeah. I was sick recently, and I was watching some old episodes. And then when God walks into the room and he's trying to make a pitch, he goes, "I'm not here to tell you about Jesus. You know about Jesus, right?" Like I'm trying to kind of evangelize, ED here for the audience, right? But there's some specifics that we can get into that I think would like actually answer a lot of your questions. Because what I did in this case to kind of expand the kind of stochastic processes that you can work over, I added like these stopping times, and the stopping times would be informed by the force of mortality that you're talking about, right? And then you could actually kind of have a more general process. So I think we can, like, I think there is a way to do it. I think like everything you're saying is correct, and that's where the subjectivity